Good morning, students. I'm Suneetha, Assistant Professor of Chemistry from Kakatiya Government College, Hanamkonda. Today we are going to discuss about alkenes, third part. Here we are discussing about the chemical properties of alkenes. We have already started. Few of the properties are finished in the previous session, and today we are going to discuss the rest of the chemical properties of alkenes. So, alkenes is a subtopic of cyclic hydrocarbons, which is a part of the second unit organic chemistry of first semester of BSc students, BSc first year students. So now let's discuss about the alkenes chemical properties. Continuation. Uh, Today's first property is hydroboration. Hydroboration. Hydroboration is addition of borane. Borane is nothing but BH3. Addition of borane to alkenes is called hydroboration. So BH3 adds to double bond of an alkene to give an alkyl borane. So in alkaline medium, hydrogen peroxide oxidizes alkyl boranes to alcohols. So here alkyl boranes are obtained by the addition of borane to alkenes. And these alkyl boranes, in other words, they can be converted to alcohols. They can be converted to alcohols in the alkaline medium with the help of hydrogen peroxide. Hydrogen peroxide is an oxidizing agent which oxidizes alkyl boranes to alcohols in alkaline medium. So the overall reaction is regioselective. Regioselective. So about this regioselectivity, we will discuss in higher sections. Okay. So the diborane adds to alkenes with anti-Markovnikov orientation to form alkyl borane, which upon oxidative cleavage gives anti-Markovnikov alcohol. So here the addition of borane or diborane to alkene is in anti-Markovnikov orientation. This we have already discussed what is meant by anti-Markovnikov effect or peroxide effect or Kharash effect. Okay, so here diborane is B2H6, which is a dimer of borane, which is a dimer of borane. Borane is BH3 and the dimer of BH3 is B2H6, that is diborane. And this borane is best stabilized. This borane is best stabilized by Lewis acids like THF, THF, tetrahydrofuran, and this one um, it, this is diethyl ether, and this is uh, diethyl amine NET2, diethyl amine. This is diethyl ether. ET2, that is two ethyl groups and oxygen. That is nothing but C2H5 OC2H5. That is ether, diethyl ether. This is C2H5 and C2H5. C2H5 and C2H5. This is diethyl amine. So, this BH3, it will be stabilized by Lewis bases like THF or diethyl ether or diethylamine, etc. So this is about the reagent, that is diborane or borane, what we are going to add to alkenes. Now let us see the reaction. So this is alkene to this diborane B2H6 or BH3 in THF. BH3 and THF. BH3 is more stable in the form of either B2H6 or BH3THF. Okay, tetrahydrofuran this is. So, is added to this alkene. Then what happens from BH3? H goes to one carbon and BH2, the rest of the part of the BH3 goes to another carbon. So, you can see here a new sigma bond is formed in between one carbon and one doubly bonded carbon. So one carbon and hydrogen, and the other carbon, to this other carbon of the alkene, BH2 group gets added. Thus here also another sigma bond is formed. So two new sigma bonds are formed here. That is nothing but addition reaction, and the pi bond present in between the two carbon atoms is broken. So when this alkene, it combines with diborane or BH3 EHF. Then what happens? We alkyl borane and addition product is obtained. This alkyl borane it undergoes oxidative cleavage. That is oxidation with the help of hydrogen peroxide as an oxidizing agent in presence of a base or alkali to form an alcohol. So BH2 becomes OH here. Okay. So this is the addition of diborane to alkanes. Now let's see the mechanism of this reaction. This is alkene, and from BH3, H goes to one carbon and BH2 goes to another carbon. Okay, so here this is transition state where this BH3 gets added to alkene. Then what happens? This pi bond slowly breaks and the two new sigma bonds will be formed, and this sigma bond present in between B and H also breaks. So this sigma bond breaks, here one pi bond breaks, and these two new sigma bonds are formed. Thus we will get alkyl borane. This is alkyl borane which is produced, which undergoes in presence of an alkaline medium with the help of hydrogen peroxide undergoes oxidation to form alcohol. So, in alkaline medium, hydrogen peroxide it oxidizes alkyl boranes to alcohols. Now, here borane adds to the double bond in a concerted single step. Concerted in a single step. Concerted manner, single step. One step the reaction takes place, we mean to say, and boron adds to the less hindered or less substituted carbon. Boron, that is the BH2 group, it goes to the carbon with the less number of hydrogens. More number of hydrogens are less substituted carbon. Less substituted carbon means the carbon which contains less number of substituents, and the hydrogen adds to the more substituted carbon. Then this is nothing but anti-Markovnikov of addition. So this leads to more stable transition state in which partial positive charge goes to more substituted carbon. Okay. Now let's see the reaction. Anti-Markovnikov of addition. Here we considered this is 2-methyl 2-butane. 2-methyl 2-butane. To this BH3 is added. BH3 is added. So there are two possibilities. If from this BH3 H goes to this carbon, what happens? If H goes to this carbon, what happens? Those transition states we can observe here. So from this BH3 H, if it goes to this more substituted carbon and BH2 goes to less substituted carbon, this is the transition state of it. In the other words, if H goes to less substituted carbon and BH2 goes to more substituted carbon, this is the transition state produced. Now we can compare the stability of the transition states produced. Okay. So in this transition state, positive charge is present on the tertiary carbon. In this transition state, positive charge is present on the secondary carbon. And we know that the tertiary carbon is more stable when compared to primary secondary or primary carbons. So as the positive charge is present on the tertiary carbon, it is this transition state is more stable when compared to this secondary this transition state where the positive charge, the partial positive charge is present on the secondary carbon. Therefore, the first one, it gives more stable product, more stable product. This is nothing but anti-Markovnikov's addition, where the positive part goes to the carbon with less number of hydrogens and negative part of the reagent goes to the carbon with more number of hydrogens, more number of hydrogens. So, in this way, we get this product as a major product. Hence, we can say that the addition of BH3 or diborane to alkene is with anti-Markovnikov orientation to form alkyl borane. To form alkyl borane. Okay. So this alkyl borane produced undergoes oxidative uh, oxidation in presence of alkaline medium with hydrogen peroxide to give an alcohol. To give an alcohol. This is anti-Marconi cups product which is produced. So this undergoes addition with B2H6 to form alkyl borane, which upon oxidation with H2O2 in presence of a base to form an alcohol. To form an alcohol. So this is about the anti-Marconi addition of diborane or borane to an alkene. Now, mechanism of oxidation of alkyl boranes to alcohols. So, alkyl boranes, how they get converted to alcohols is given here. Okay. So, this is hydrogen peroxide. Hydrogen peroxide, H2O2. A peroxy bond is present here. Now, here, in presence of a base, it gives this ion. This ion, HOO minus ion. This ion is produced. Okay. So this ion, that is from this hydrogen peroxide, one proton is abstracted by the base. Thus, water is eliminated, OH and H plus, OH minus and H plus in the form of water. The rest of the part, that is a negative ion, is left behind. This negative ion, it goes. Let us see where this negative ion. Okay. This negative ion, this OOH minus, this negative ion, it goes and attacks the boron atom of BH3, boron atom of BH3. That is boron atom of alkyl borane, let me say here, alkyl groups, alkyl borane. Okay, so boron atom of alkyl borane, it attacks. Then this bond is formed in between this oxygen of hydrogen peroxide and boron atom of alkyl borane. Alkyl borane. Okay. Then this in this structure, the boron atom, it suffers with the uh, negative charge because it is surrounded by four bonds. That is four electrons surrounding this boron. Boron belongs to third group, as it is having four electrons surrounding it. It means it will definitely carry um, negative charge. So a negative charge is present on boron atom. Then what happens? This alkyl group, this alkyl group, it gets transfers to this oxygen, whereby the bond between O and O breaks and the OH minus ion is lost. Thus, here this is nothing but a kind of a rearrangement. Okay. Then what do we get? Here boron with two alkyl groups and OR. This O and this R. And OH is lost in the form of OH minus. OH minus. Okay. Now, let us consider this as the substrate in the next step. See, R2BOR. This is R2BOR. Now in this stage, similar attack of this HOO minus ion on this boron. Once again, we will get such type of ion where boron suffers with a negative charge. Then what happens? This R, one of the alkyl groups, gets migrated to oxygen and OH minus is lost. Once again, we will get this. That is, this is ROB bond. Two. In this, only one ROB bond is present. Here, ROB. This is alkyl group, this is oxygen, and this is boron. Another bond is also formed in this. Okay. So, next step, what happens? This is taken as a substrate. You can see this. Okay. B, OR, and R. C. B, this is alkoxy group, another alkoxy group, this is alkyl group. Now, and onto this boron atom, the same ion which is produced from peroxide, hydrogen peroxide, attacks once again, similar attack. Okay, then what happens? We will get a new bond is formed in between this oxygen and boron. You can see here, and boron suffers with a negative charge, and another alkyl group, it gets migrated to oxygen and OH is lost in the form of OH minus. Then we will get B, that is trialkoxy boron. You can see OH, R-O bond, R-O bond, R-O bond. These are all alkoxy groups. Three alkoxy groups to boron atom. Okay. So This is trialkoxyborane. This trialkoxyborane, it undergoes hydrolysis. It undergoes hydrolysis to form alcohol. Here, hydrolysis takes place. H, H and OH, water molecule. So H goes with the RO group, that is alkoxy group. Here also H goes with RO group, alkoxy group, and here H goes with RO group, that is alcohol. So 3 moles of ROH, that is alcohol, is produced. And what is left behind? From each water molecule, OH minus is left behind. OH, 3 hydroxide ions and this boron. That is nothing but H3BO3 or BOH taken thrice. Like that also we can write BOH taken thrice or H3BO3, that is boric acid. Okay. So alcohol is produced in this way from alkyl borane. So we started with alkyl borane. This alkyl borane, 3 alkyl groups and boron. Okay. So there is alkyl borane. It uh, undergoes oxidation with hydrogen peroxide in presence of a base to form alcohol. This is the reaction. So these are the different stages involved in the formation of alkyl boranes to this is alkyl boranes to alcohols. And we should definitely see here there is no bond present in between this boron and oxygen actually initially. So here R3B is present and this OOH, that is HOO minus ion, it goes and attacks this boron. Okay. Similarly on all these structures, here no bond should be there. See here it is not there. Okay. So here no bond should be there. Initially this is attack of the O minus ion, that is HOO minus ion to boron. Here also no bond should be there. Okay. Right. This is about hydroboration. Next one. Next property, oxidative cleavage of alkenes. Oxidative cleavage of alkenes. That is another name given to this property is ozonolysis. Ozonolysis. That is addition of ozone followed by hydrolysis. Now what happens here? Let us see. So ozone cleaves double bond and forms carbonyl compounds. Carbonyl compounds are nothing but aldehydes and ketones. So wherever double bond is there, if we add ozone there, what happens? It cleaves this double bond and forming the carbonyl compounds. Now let us see this reaction. So here we considered general alkene. To this ozone is added. Ozone is added. Then what happens? Here the bond breaks and one oxygen is given to this carbon and another oxygen to this carbon. Okay, here the bond breaks. We can see the product. R C double bond O R. See here. Another one. R C double bond O H. R C double bond O H. So this is ketone and this is aldehyde. So we may get two ketones and two molecules of aldehydes also, depends upon the initial alkene we have considered. On ozonolysis we may get either one ketone and one aldehyde or two ketones or two aldehyde molecules also. Okay. So now let us consider this reaction mechanism. So ozone reacts with an alkene to form cyclic compound that is called primary ozonide or malozonide. Primary ozonide or malozonide. And the small ozonide or primary ozonide is quite unstable and it has as it has two peroxy linkages. I'll show you the diagram, that is reaction mechanism in the next slide. So it is quite unstable as it has two peroxide linkages. Then what happens? It rearranges rapidly to form an ozonide. And the ozonides are reduced by mild reducing agents like zinc or dimethyl sulfide, etc. to form the carbonyl compounds. Now let me show the reaction here. So here let us consider an alkene. Now ozone molecule is getting added. With the help of this pi bond, it forms a bond with one of the oxygens of ozone, and this with the help of this negative charge, this oxygen, it forms a bond with this carbon. Now let us see the malozonide produced here. Malozonide. So this carbon, it has O linkage and a cyclic compound is produced. You can see here a cyclic compound is called, which is known as primary ozonide or malozonide, where two peroxy bonds are present. What is peroxy bond? We said ovo bond is called peroxy bond. So oxygen oxygen, one peroxy bond, oxygen oxygen, two peroxy bond. This molecule is highly unstable. So then what happens? It undergoes rearrangement. Rearrangement takes place. Due to rearrangement, what happens? We will get, this is rearrangement transition state. We will get this compound. This is known as ozonide, where only one peroxy bond is present. Okay, so this is ozonide. This ozonide, it undergoes, this ozonide, it undergoes mm, reduction, reduction with a mild reducing agent like dimethyl sulfide or zinc dust sometimes to form carbonyl compounds. So the bond here breaks. Okay, here one carbonyl compound, and here the bond breaks. This bond breaks and this bond also breaks. Here also bond breaks. So two molecules of carbonyl compounds are produced. Two molecules of carbonyl compounds, and the other product is dimethyl sulfoxide. Dimethyl sulfoxide, DMS. Okay. Now let us see the example here. Dimethyl sulfur, dimethyl sulfide, DMS. Dimethyl sulfide, methyl group, and yes, sulfur, sulfur is fine. Okay, dimethyl sulfide. And now this is ozone. First step, ozone is added. Then the bond here breaks, and one oxygen to this part, another oxygen to this part, oxygen here, oxygen here. Okay, then this is first first example, specific example. Here we considered hexene. Hexene. This hexene, it undergoes addition with the ozone, followed by reduction with the DMS to form this compound. Okay. Now let's see another example. This is methyl. This is cyclohexene. This is methyl cyclohexene. Methyl cyclohexene. Okay. Now undergoes ozonolysis. Ozone addition followed by reduction. That process is known as ozonolysis. Then we get this product. So simply the bond here breaks, pi bond here breaks, and one oxygen to this carbon and another oxygen to this carbon. That is what happening here. Okay. So this is called ozonolysis reaction. Ozonolysis reaction. So with the help of ozonolysis products of ozonolysis, we can find the position of the double bond in the alkenes. Now next, we are going to discuss about dienes. Dienes. So what are dienes? Alkenes which contain two carbon-carbon double bonds. Two. Here, this point we should remember. Carbon-carbon double bonds. Two are present. Then they are known as dienes. Di means two, ene means double bond. Okay. So alkenes that contain two carbon-carbon double bonds are called dienes. So these double bonds, how they are present? How they are present, that is important. So double bonds in diene have the same properties of simple olefins. So these dienes are also having the similar properties like that of olefins, that is alkenes. But in some of the dienes, the properties are different due to second double bond. But few alkenes, dienes, they will be having different properties because of the presence of the second double bond. Okay, so now these double bond dienes, how they are classified? What are dienes? We said dienes are the alkenes which contain two carbon-carbon double bonds. Now, how these dienes are classified? Let us see. So, dienes are classified into three types. One is conjugated dienes, second one is isolated dienes, third one is cumulated dienes. Okay. Now, first one, conjugated dienes. So, dienes are divided into three groups based on the position of the double bonds. Okay, where the double bonds are present, how these two double bonds are oriented in the alkene. Based on that, they are classified into three types. One is conjugated dienes, second one isolated dienes, third one is cumulated dienes. The first one, let us discuss, that is conjugated dienes. So what are conjugated dienes? Conjugated dienes are having alternate double bonds with single bond separation. So when a diene contains two double bonds alternatively with the separation of a single bond, then they are called conjugated dienes. So let us consider this example. This is the diene. Here double bond is there, separated, two double bonds are there, separated by one single bond. So one double bond, one single bond, one double bond, again single bond, again double bond. Like this, if it goes, this is known as conjugated diene. Conjugated diene. So this uh, conjugated alkene if more number of double bonds are there. Otherwise, it is only two double bonds are there separated by one single bond, then it is known as conjugated diene. Okay, only two double bonds, diene. More number of double bonds are there separated by a single bond, then it is conjugated alkene. Okay. So it is a diene which is called conjugated because two double bonds are separated by one single bond, or alternate double bonds are present in a diene, then it is known as conjugated diene. Now this is a cyclic example, conjugated diene. So this is the cyclohexadiene. This is cyclohexa, 6 carbons, di means 2, ene means double bonds. So cyclohexadiene. These are the examples for conjugated dienes. Now, next one, let us see isolated double bonds. Isolated double bonds. In a diene, if double bonds are separated by more than one CC single bonds, then they are called isolated double bonds or isolated dienes. Okay. So, what are isolated dienes? In these isolated dienes, two double bonds are separated by more than one CC single bonds. If they are separated by one single bond only, then they are called conjugated dienes. If they are separated by more than one single bonds, then they are called isolated dienes. See, diene it is because two double bonds are there. Two double bonds are separated by more than one. Here two are there. Okay, more than one. There may be 3, 4, 5, any single bonds. Okay, any number of single CC single bonds. Then it is known as isolated diene. This is an example. Another example here we can see. This is also cyclohexadiene, but the position is different. Position of double bonds is different. Okay, so here one double bond separated by two single bonds. Another double bond. This side also you can consider double bond. Two single bonds, one side double bond. Therefore, these two double bonds are separated by two single bonds. Therefore, it is also an example for isolated diene. Now, last one. Cumulated diene. What is cumulated diene? Let us see. Dienes having double bonds sharing one common carbon. Dienes, see, diene having double bonds sharing one common carbon. That is, two double bonds are not separated by any single bond. They are continuous double bonds. See, you can see. Okay, continuous double bonds without intervening single bonds. Two double bonds are continuously present. In between the two double bonds, no single bond is present. Then it is known as cumulated diene. Cumulated diene. Okay, so dienes having double bonds sharing the common carbon, that is continuous double bonds without intervening single bonds, are called cumulated double bonds or cumulated dienes. Okay, so these are also called allenes. What is the other name given to this cumulated diene? Allene. Allenes. Okay, allenes. So this is uh, cumulated diene. Two double bonds without the separation of a single bond, and two double bonds they share one common carbon. Continuous double bonds when they are present without any separation of a CC single bond, then it is called cumulated diene, and which is also known as allene, which is also called allene. Okay, now let's see the reactions of conjugated dienes. What are the different reactions which we come across for conjugated dienes? Let's see. So properties of conjugated dienes are different from single alkenes in the following ways. So, what are the different uh, ways in which these dienes differ from the alkenes? See, conjugated dienes, they are more stable. They are the preferred products of many elimination reactions. They undergo both electrophilic and free radical 1,4 addition reactions. Generally, we know that alkenes undergo electrophilic addition reactions, but here this conjugated dienes, they also undergo electrophilic as well as free radical addition reactions. And in the elimination reactions, these are preferred. And next one is this conjugated dienes are more stable when compared to simple alkenes. Here let us consider an example, that is 1,3-butadiene. 1,3-butadiene. So this one 1,3-butadiene. Okay. 4 carbons buta. First carbon and third carbon double bond is there. The 1,3 buta. Di means 2. Ene means double bonds. So this is 4 carbon alkene, that is butane. Two double bonds are there, therefore it is butadiene. Where these double bonds are present on the first and two, 1 and 2 carbon atoms in between, and 3 and 4 carbon atoms. So lowest number we should mention 1 and 2. Lowest number is 1. 3 and 4. Lowest number is 3. Therefore it is 1 comma 3 butadiene. So 1 comma 3 butadiene is considered as the best example or the simplest example for conjugated diene. Okay. Now this butadiene, let's see. 1,3-butadiene, it undergoes addition with HBr and produces a mixture of products. There 1 comma 2 and 1 comma 4 addition products are produced. 1 comma 2 addition in the sense hydrogen goes to first carbon, Br goes to second carbon. And 1 comma 4 addition in the sense H goes to first carbon and Br goes to fourth carbon. Okay, addition products. So the yield of 1, 2 and 1, 4 addition products depends on reaction temperature. So which product is produced, the yield, the amount of the quantity of 1, 2 and 1, 4 product is dependent upon the reaction temperature. So generally the reaction at low temperature, that is at about minus 80 degrees centigrade, minus 80 degrees centigrade produces a mixture containing 20% of 1,4 addition product and 80% of 1,2 addition product. At low temperature, the major product is 1,2 addition product, minor product is 1,4 addition product. But at the reaction at high temperature, that is at about 40 degrees centigrade, it produces 80% of 1,4 addition product, that is major product, and 20% of 1,2 addition product. So as the temperature changes, what is that happening? The minor product at a low temperature becoming major product at high temperature. Okay, so the minor product at low temperature is this one. This one, 1,4 addition product is minor product at low temperature. Whereas at high temperature, this 1,4 addition product has become a major product. Okay, so this one we will discuss here. Okay, let us see. This is 1,3-butadiene. To this we have added HBr at minus 80 degrees centigrade and 40 degrees centigrade. At minus 80 degrees centigrade, what did we say? 80% of 1,2 addition product is produced, that is in this at this carbon atoms, that is the first double bond, let me say 1 and 2 carbon atoms, in between these two carbon atoms double bond is there, that is broken and H and Br are added over there. Okay, so next one, 20% of 1,4 addition and H goes to this carbon, Br goes to this carbon and double bond shifts. Okay, so this is the minor product, this is major product. 1,2 addition major, 1,4 addition is a minor product at minus 80 degrees centigrade, that is at low temperature. If it is at about 40 degrees centigrade, at about 40 degrees centigrade, that is at high temperature, 1,2 addition product is 20%. See here 80, here 20. That is, and 1,4 addition product is 80%. This is the major product at high temperature. This is the minor product. Okay. So this is about the addition of HBr to 1,3-butadiene at high and low temperatures. High and low temperatures. Now, the production of products originally isolated from the low temperature addition and which are determined by the rate of addition of HBr. Rate of addition of HBr. For high temperature addition, the products are determined by the equilibrium between the two isomers, how they are isolated, and how do you say that which is major product and which is minor product. That can be given by this. Okay, and the activation energy leading to 1,2 addition product is lower than 1,4 addition product. What is activation energy? Activation energy is nothing but the amount of energy, the excess amount of energy needed to reach the threshold. Therefore, as the activation energy is more, the rate of the reaction is less. Activation energy is less, the rate of the reaction is more. So here the activation energy is for a 1,2 addition product is less, whereas that of 1,4 addition product is more, we said. So this concept is represented here with a diagram. See, this is 1,3-butadiene. To this 1,3-butadiene, okay, say this. This is one. Here, okay, should be here. Okay, the 1,3-butadiene only we consider, and HBr is added. HBr is added. H plus H goes to first carbon. Then what happens? We will get a secondary carbonium ion is produced. The second carbonium ion is produced, and it's due to mesomeric effect. This pi bond gets shifted over here. Then this last carbon, fourth carbon gets the positive charge and a primary carbocation is produced. This is secondary carbocation, this is primary carbocation. Therefore, secondary carbocation is more stable, we know, when compared to primary carbocation. Okay, so here if we consider the resonance hybrid of these two structures, it will be like this. H is added over to this carbon, and this is resonance hybrid where the positive charge is present on all the three carbon atoms. And then this resonance hybrid effect and goes addition with the Br minus. If this Br minus goes to this carbon, 1,2 addition product, Br minus goes to this carbon, we will get 1,4 addition product. 1,2 addition and 1,4 addition products produced. Okay, so this is the preparation, addition of HBr to 1,3-butadiene. Okay, now let us see the reaction energy diagram of this reaction. This is potential energy on the y-axis and the reaction coordinator progress of the reaction on the x-axis. And here 1,2 addition product, activation energy is less. Activation energy is more. 1,4 addition, activation energy is more. And here the 1,4 addition product is obtained. Okay, addition product. So activation, low activation energy for 1,2 addition product and high activation energy for the 1,4 addition product. So this is the reaction energy diagram for addition of HBr to 1,3-butadiene. Now another reaction of dienes, conjugated dienes especially, is Diels-Alder reaction. Very, very important reaction, Diels-Alder reaction. In this Diels-Alder reaction, the conjugated dienes, they undergo important cycloaddition reaction. Addition reaction with simple olefins. Olefins means alkenes are substituted olefins under thermal conditions to produce six unsaturated products. This reaction is called Diels-Alder reaction. Diels-Alder reaction. This is also known as 4 pi 2 pi reaction or 4 plus 2 pi reaction. 4 plus 2 pi addition. 4 pi 2 pi or 4 plus 2 cycloaddition reaction it is also called, because a 4 electron contributor is called diene. This one 4 electrons, 2 pi bonds are there, each pi bond is made up of 2 electrons, so altogether 4 pi bonds are there, therefore it is called diene. And the 2 pi electron contributor, the one which donates, which contributes 2 electrons, is a diene, that is known as dienophile, this one. So First one is 4 pi electron contributor is called diene, this one. And second one participating in this reaction is a 2 pi electron contributor, that is known as dienophile. And the one which likes diene is called dienophile. Phile means loving, liking, seeking. So this one seeks diene, therefore it is called dienophile. So diene plus dienophile gives rise to a cyclic adduct order reaction. Unsaturated cyclic compound, unsaturated cyclic compound. That the cyclic compound will be having six member, four-member diene and two-member dienophile combines to form a six-membered ring. So here what happens? Let us see the reaction. So it is a reaction. This Diels order reaction is a reaction in which two unsaturated molecules undergo addition to form a six-membered cyclic addition product. Adduct is addition product. So the two pi bonds are transformed into two new sigma bonds during the addition. So during the addition reaction, what is that happening? Two pi bonds are transformed to, that is, they are converted to two new sigma bonds. Two new sigma bonds. And the diene system contributes 4 pi electrons and dienophile contributes 2 pi electrons. Therefore, it is also called 4 pi plus 2 pi are simply 4 plus 2 cycloaddition reaction. 4 plus 2 cycloaddition reaction. Now, this is a concerted, that is it takes place in single step mechanism. So let us see this. 4 pi electrons contribute a diene and 2 pi electrons contribute a dienophile. They combine to form 4n plus 2, 4 plus 2 or 4 pi 2 pi addition. Cycle addition takes place. You can see the uh, six-membered cyclic transition state which is forming. Here what is that happening? This, with the help of this pi electrons, a bond is formed in between this carbon and this carbon with the help of these electrons like this. And with the help of these two electrons, a bond is formed in between this end of this carbon and this carbon. This forms a sigma bond here and this forms a sigma bond here, and this pi bond moves over there. Shift of this pi bond towards these two carbon atoms. You can see here. This is the cyclic six-membered compound produced. So presence of electron donating groups in dienes, presence of electron donating groups in dienes, and electron withdrawing groups like CHO. Okay, withdrawing groups in dienophiles increase the rate of the reaction. So it should have electron withdrawing groups, it should have electron releasing groups. Then the reaction proceeds faster. Okay, increases the rate of the reaction. So here example, another example, this is dienophile. Then here bond is formed in between these two, this carbon and this carbon, with the help of this pair of electrons. And with the help of these electrons, a bond is formed in between this carbon and this carbon. Thus, a cyclic adduct is formed and the shift of these electrons towards the adjacent cis single bond. So here we will get addition product, that is adduct, is produced. Another example here we have given, this is 1,3 butadiene, this is maleic anhydride, and we will get 1,3 butadiene maleic anhydride adduct is produced. Adduct. Another example, this is 1,3 butadiene, this is acrylonitrile, that is electron withdrawing group. Here also diene, cyclic diene we consider, electron withdrawing, this dienophile with electron withdrawing group, and predict the product. These are all the different reactions of Diels-Alder reactions. Okay. Questions related to our today's topic. So this is related to Diels-Alder reaction. Now next questions. Discuss 1, 2 and 1, 4 HBr additions of 1,3-butadiene. Next question is give an account of Diels-Alder reaction. We should discuss about the Diels-Alder reaction. And here few reactions which are related to Diels-Alder reaction only. Other reactions given. Here we should predict the product, give the product in the following reaction. So simple here. This pi bond breaks and a sigma bond is formed in between these two carbon atoms. This pi bond breaks and a sigma bond is formed in between these two carbon atoms, and this pi bond shifts. That is the product produced. This we can easily give. So Diels-Alder addition is a popular synthetic reaction used for the synthesis of large number of biologically active compounds. Okay. So next questions. Mm, in these reactions, we should predict the products. This is an alkene and addition of borane followed by oxidation. That is, alcohol is produced, anti-marconic of addition takes place. This we have already discussed. And this is another reaction, that is metachloroperoxybenzoic acid. This is nothing but trans addition of paracids via epoxidation. And next one is what is ozonolysis? Reaction with simple reducing agents like dimethyl sulfide or zinc. And here we should predict the products ozone and dimethyl sulfide. Here the bond breaks and one oxygen here, another oxygen here. So 2 moles of acetone we get. And this is nothing but osmium tetroxide. That is syn hydroxylation takes place here. Syn hydroxylation, and to this double bond syn hydroxylation takes place, and one OH here, another OH here we get. This is osmium tetroxide, syn hydroxylation. And next one is this one. This is nothing but 1,3-butadiene. That is a conjugated ion to this HBr addition at minus 80 degrees centigrade and 40 degrees centigrade. So 1, 2 addition and 1, 4 addition. Two products here we get. One is major, the other one is minor. And here also 1, 2 addition product and 1, 4 addition product we get. One is major product and one is minor product. Thus we should write. Okay. These are the questions related to today's topic. Another one. This one, predict the products with reaction related to today's our topic, that is diborane or borane addition, borane THF addition followed by oxidation with hydrogen peroxide in presence of a base, that is an alcohol will be produced here in this reaction. So what is that we should predict? So next, these are the two substrates onto which hydroboration takes place. So final product obtained is the alcohol that we should predict here. Okay. And these are the some other reactions of Diels-Alder reaction. Some other simple examples Diels-Alder reaction. Okay. Another one, classify the following dienes as conjugated, isolated, and cumulated. Whether it is conjugated or isolated or cumulated ion. So this one, two double bonds separated by more than one single bond is a single bond, therefore it is isolated ion. And this one, two double bonds separated by one single bond, nothing but conjugated ion. And these are the two double bonds continuously present, therefore it is nothing but the cumulated ion. Okay. Thank you. We will continue with the another topic of the cyclic hydrocarbons. One and all.